Hi class, this is the second half of the lecture for today. So I apologize, I'm a little under the weather. So if I'm sound a little monotone, that's why. Okay, so we should have covered some of the basic principles of stimulation. So what exactly makes tissues excitable, and some of the parameters that we should consider when we're designing any instruments that effectively have to stimulate excitable tissue. So what's going to follow here is two examples of stimulators. There's all sorts of stimulators that we covered in the previous slides. I think I had a table which you should have seen in class. So let's go over two here. This is actually a good segue for in 2 weeks when we have a visitor from Advanced Bionics. So they actually work on cochlear implants. Okay, so now that you have some background into how to stimulate tissue, so one application would be for cochlear implants. So for people that have lost some function in their hearing. All right, so their cochlear implants are basically able to help people regain hearing, and the amount of hearing loss it varies, and even the devices vary depending on the severity of the disease. But generally, cochlear implants basically look like this, where you have some sound processor, microphone as well, and then you have some wireless link here that communicates with some implant that's inside the body. So let's go over all of it. So basically, this thing over the ear, that's the sound processor. So that's basically a microphone that captures sound that the user is hearing. Then that is digitized and sent to this transcutaneous coil. So within here, there's power, but there's also data transmitted, and that data is the digitized signal from from the sound processor. That gets then communicated to an implanted transcutaneous coil in implant, and then that terminates to basically a coil that is implanted inside the cochlea of this person. So if you recall from the auditory system lecture, within the cochlea, that's a fluid-filled cavity. Sorry. And within there you have the basilar membrane, and then you also have the hair cells that interact with the auditory nerve. So this electrode here, it has a couple of electrodes actually along the length here as it's coiled up into the shape of the cochlea. These electrodes are intermittently stimulating the auditory nerve along the cochlea. Okay, and so how exactly does it do that? Here's actually a comparison of various types of cochlear implants. There are three types here. There's a nucleus freedom, the Clarion, and the Med-L. And it's just comparing like the external unit. So that's again the sound processor. I'm not gonna get into the processing strategies here. That's something for 603, I believe. And this number of maps metric here, that's just basically how exactly the sound that's being captured by this microphone is then interpreted, or I should say converted to electrical pulses that stimulate the electrodes, or I'm sorry, the auditory nerve. This is giving you some data rate and RF carrier frequencies for this link, and but as you can see, basically you have a microphone, some front end circuitry, which then gets processed and sent to the electrodes. So again, this is just to compare. Okay, one of the key, and what I should say is, I'll go back here. There's a lot of research that's done within each of these kind of boxes here, right? For basically a lot of processing strategies that you can talk about, like how exactly do you filter out the signal so that what the person's hearing is high fidelity, but not inaccurate. there's some research that's been done on the actual electrodes, the stimulation rate, the waveforms. Um, all of that is pretty well covered in the literature. But what I wanted to focus on here is the actual electrodes, because they're pretty unique given the, I guess, challenging anatomy of the cochlea. Um, so here's an example of this where you typically have some silicone encasing and you have some exposed electrodes, which then can be curled up into the shape of the cochlea. And that's important because you remember you have to minimize the distance between the electrodes and the auditory nerve in this case. Notice how a lot of these electrodes, they have little wires or leads. They are kind of zigzaggy. That's to accommodate for the bending that is necessary for this electrode to sit inside the cochlea. So there's a couple of things you have to keep into consideration. The other thing too is the material here. I believe it's silicone, but it has to be relatively easy to implant into the cochlea. So we'll get to some material considerations, I think, next week when you're designing these kinds of devices. Here's another example of some electrode arrays for cochleas. This is just reiterating like the actual connectors to the electrodes. You know, they have to be kind of snake-like so that you accommodate for the bending of this device. Here's a good picture on the bottom here of how this is actually implanted in a human. So this is the cochlea shape. This is the electrode, and you can see that it has to basically, as it's inserted, it has to form along this shape. And so that's something that you have to consider when you're designing these things. So at the top here, over here are the electrodes that are going to be sitting in the cochlea, and these are all the leads. They're individual wires that are connected to the implant, where the RF link sends the stimulating pulses. So each of these wires are effectively a given pulse. In this case, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrodes. So one of the important considerations to kind of think about is that you want this to stimulate as much as possible along the length, or I should say circumference, of this cochlear implant. So if you have smaller electrodes, the better, because you're able to then stimulate more sites, and you're able to mimic the number of stimulating sites in a natural cochlea. Here are what the devices look like. Again, this is the implant, this is the electrode, this is the speech processor right here. And so again, we'll hear more about this from Advanced Bionics, I believe, in 2 weeks. Alright, so another application is retinal implants. So, instead of restoring hearing, how can we restore vision? I should say, unlike cochlear implants, which are very, very well developed, retinal implants are also developed, but it's really until recently that we really start to see that these devices can make a big impact on people that are blind or have some loss in their eyesight. Okay, so I'm not going to get too deep in the weeds here, just because retinal implants are actually very, very complicated. The other reason is because there should be a presentation from a student group on this. Alright, so retinal implants are able to help people with vision issues, and there's basically two types of implants. There's this thing called epiretinal and subretinal. But regardless of the type, basically the way this device works is you basically have to acquire an image, and this is kind of where they differ a little bit in how they do that. And then that image is then converted and digitized to create stimulating waveforms. And what's important here is that both of them are located at the retina, so towards the back of the eye, near the um, near all of the rods and cones. But the main difference between epiretinal and subretinal is that the subretinal is actually within the retina, so within the layers of the retina. So obviously that's uh, very invasive compared to epiretinal. They're both invasive. And these are basically right directly near the bipolar cells that we talked about earlier, and the photoreceptors. The epiretinal sits on the surface of the retina. Okay, so what's the difference here? Let's go over epiretinal first. So the way this works is there's an external camera. Usually you'll see it as some form of glasses where you'll collect the image and then that gets processed by some processor and then gets converted to stimulation waveforms, which just like the cochlear implant gets sent via an RF link. And then there is electrodes. So unlike the cochlea, where there's this kind of helical looking electrode, there's actually this pad that has multiple electrodes. In this case, there are 16 electrodes. And for the epiretinal implant, it's on the retina, the surface of the retina. And the processor converts the image into stimulation waveforms at each of these individual electrodes here. And there is, again, a whole slew of research on how to convert those images to specific stimulating waveforms at the retina. So that's how epiretinal implants work. Okay, here's an actual view of it. So one of the most developed devices is the Argus 2 from Second Sight. They're actually located around here in the valley. And you can see that, here's the electrodes. Here you have many more electrodes. That's the gold looking pads here. And in this case, they have 60 electrodes to have more stimulating sites. And so these already have been tested clinically, and so they're able to basically improve motion detection and navigation for some of these patients that have lost some vision. One thing to consider is that the visual field is limited by the area of the stimulation on the retina. So in an ideal world, you'd be able to stimulate, over the whole area of the retina. But obviously, you would need some. That has its own challenges in terms of implantation and I guess practicality of how to actually place that on the retina. All right, subretinal implants. These are a little bit different in the sense that there is no external camera that captures an image and then converts it to a bunch of stimulation waveforms. The way this works is there's actually a array of microphotodiodes. So those are diodes that conduct electrons when light hits them. And so you have basically, without the camera, you have this implant that is implanted underneath the retinal layer here, near all of the bipolar cells. And when light hits it, remember that the retina is transparent. So when light goes through the retina and it hits the microphotodiodes, they create stimulation waveforms, which then stimulate the photoreceptors in the eye. So these are mainly used for more advanced diseases, where simply stimulating the retina won't do in terms of regaining some visual function. So here's actually one of the devices. So you have this microphotodiode array. It's fabricated using CMOS, and in this case there's 150 pixel elements. So right here, this is what's implanted within the eye. Right, so sorry, I forgot to distinguish. So the photodiode array, that's what captures the image. So within a 3 by 3 millimeter area, you have 150 pixel elements, which is great because you're able to capture a lot of image. But the downside here is that the electrode array that you are basically using to stimulate is only a 16 electrode array. So obviously, if you had an electrode array that is on the order of these many elements, you're able to get better pictures, better images for the patient. Here are just some examples of different stimulation waveforms for each of the electrodes. I believe this one is for this device here. It's only showing 4 electrodes, but you can see that. I guess the point of this slide is to just show you that there is a lot going on here, right? So these waveforms are not just rectangular pulses that we were talking about earlier in class. They have to consider how much energy is imparted into the tissue, how much charge, how long, and you can notice here that the repeating waveforms and the duration changes depending on which waveform you're looking at. Some of these that go negative and then go positive, there's some kind of charge balance going on there. So just what I'm kind of take home message here is that there's a lot involved in converting some signal or image, or in the case of cochlear implant, some audio signal, and converting it into a relevant stimulation waveform for the patient. You not only have to consider the threshold voltages to actually stimulate the tissue, and that goes back to considering the Rio base and the strength duration curve for some of these tissues, but it also has to do with how much energy and how much current and charge you're imparting into the tissue, and so you should have a better idea of why these waveforms are the way they are to a very general sense. Okay. All right. So the next class we're going to cover biomaterials. So some of the considerations to discuss when we're actually creating medical devices. So this will be a very broad lecture in the sense that I'm not a materials person, but we'll cover all sorts of devices and some of the things that engineers that work on those devices have to consider when they're actually implanting the device inside a body. The other thing is I wanted to go over some FDA regulations, so Food and Drug Administration. For any of you that are considering, going into biomedical engineering, this is something that you do have to consider. It adds to costs, and it can limit some of the designs that you come up with. So we'll go over that as well. Okay, thank you so much. I will see you all next week.